When a crane lifts a steel beam, a bridge supports rush hour traffic, or a radio tower resists heavy winds, these structures aren't dealing with a single isolated push or pull. They are reacting to dozens of simultaneous forces working together. We call this a force system. Before an engineer can calculate whether a structure will hold its ground or collapse under pressure, they have to define the exact geometry of that force system. The first step in analyzing any structure is determining its spatial environment. We do this by looking at the plane. Look at this 2D grid. If every line of action lies perfectly flat on this surface, we classify the system as coplanar. But if the system breaks out of that flat surface and operates across 3D planes, it is classified as non-coplanar or spatial. Establishing whether you are working in a 2D coplanar or 3D spatial environment dictates the entire mathematical approach you will use to solve for equilibrium. Let's start with 2D systems. This schematic shows a crane hook. The weight of the load is pointing straight down, while the tension in the chains pulls upward and outward. All of this happens on one flat plane. If we extend the imaginary lines of action for all three of these vectors, they intersect right here at a single central point. Because they share a plane and share a point, this is a coplanar concurrent system. Now look at this side view of a bridge. The downward weight of a truck and a car run right alongside each other. If we trace their lines of action, they will never touch. We call this a coplanar parallel system. When forces push in the exact same direction, like the vehicles pushing down, they are like parallel. When the ground supports push back up in the opposite direction, the relationship between the two groups is unlike parallel. There is also a highly specific subcase. Inside a single joint of a machine truss, you'll find forces acting in opposite directions, but lying end-to-end on the exact same line of action. These are collinear forces. In a 2D environment, the rules are strict. Forces must either cross at a point, run parallel to each other, or share the exact same line. The same rules apply when we move into 3D space. Here is a 3D wireframe of a heavy table suspended by 4 cables. These cables occupy completely different depth planes, but their lines of action all converge right here at the ceiling hook. Because they exist in 3D space, but meet at one point, this is a non-coplanar concurrent system. Next, consider the downward force of the 2 side wheels on this moving donkey cart. The wheels sit at different depths. Their lines of action project downward and will never intersect because they occupy completely separate planes. This is a non-coplanar parallel system. But watch what happens if the donkey pulls the cart forward. We've introduced a horizontal force. The system no longer shares a plane. The lines don't meet at a point, and they are no longer parallel. This is a general spatial system. Even in complex 3D environments, you are still just checking for those basic rules. Do the lines intersect, or do they run parallel across multiple axes? Let's test this. Pause the video and look at this cube. We have 3 forces mapped along different edges and faces. Run through the mental checklist. Do these lines share a flat plane? Do they cross at a single point? Do they run parallel to each other? They share no plane, they miss each other completely, and they face different directions. This is a non-coplanar, non-concurrent, non-parallel system. Running this exact checklist is how you prevent catastrophic errors before you write down a single equation. To classify any system, use this decision tree. Start at the top. Are all forces on one flat surface? This splits your problem into either coplanar or non-coplanar. Step 2. Do their lines of action cross at one point? If yes, the system is concurrent. If they don't cross, move to step 3. Do their lines run side by side without touching? This categorizes them as parallel. If they aren't parallel either, you have a general system. And if they are parallel, ask one final question. Are they on the exact same line? If yes, they are collinear. Take a screenshot of this tree. Perfectly identifying the force system is the mandatory first step for calculating structural equilibrium. It is how you ensure machines operate safely and structures stay standing.